beginning. Okay, so big data focus. So speaking about the types of big data in ASCH, it's good to know what kind of data is available already. And then a little bit, just some details of data management and storage solutions, just so you become familiar with some of the vocabulary that's used. And then I'll speak a little bit more about data preprocessing and cleaning. I said to you that, bad quality data, bad machine learning results, okay, or unreliable. Very, very important and necessary and vital stage before starting any machine learning is to do data preprocessing and data cleaning. So I'll give a little list, not very many details, we don't have time, but you should just know that these are very important issues. And then a new issue, which until now we said, it's not our problem, it's somebody else's problem. It's true. We don't have to deal with cybersecurity, but it's important to know what is cybersecurity and just to have some kind of idea of what are the threats and what kind of measures are taken in order to prevent these threats from happening and in order to preserve and protect the data. Because we can be dealing now with very, very sensitive data. We cannot say, data is data. No, this data is very sensitive and can be usable if it's being taken by somebody, or somebody is modifying it. We don't really know that they're modifying it. Pirating the data is not just to take the data, but also to modify the data. Right? So we as machine learning people, that's not our responsibility to take care of this issue, but this issue is very present, and one should know at least what it's all about. Okay, so it's just to give you some keywords and some definitions, that's all, without getting into any detail. Okay. So what are the types of big data? In particular, big data for health sciences, okay? Big data, there are many types of big data all over the world, but we look at health science in particular, right? Okay. So, the technology needs to be changed. Okay, so there are a number of sources. And I'll just give one slide of each source. So the types of data include, this is not everything, but these are the major types, what we call EHR, electronic health records, which means, I'll show you. Somebody has to do that. Has to record the data. So behind all these things, there's always something that's recording. But okay, that's something simple as there's a lot of genomic data, or we call multi-omics data. So I'll speak about multi-omics, and maybe tomorrow I'll speak about some applications more in detail. It's becoming very, very, very important data because it enables some very, very interesting research in machine learning. And then there's the whole domain of medical imaging, sensor data, social media data, which is a new source of health science data. So why these things are important? Because they can provide what we call valuable insights. Insight means understanding and analysis of what's happening. So we can have insight into health status of an individual patient, how effective treatments are, what are the effectiveness of treatments. You can imagine in pandemic type of situations, this is very important. And we can even look at the patterns of disease, how the disease is propagated. So you understand from all these things we get a lot of valuable understanding. But of course, every time you get this type of data, there are challenges in terms of data management, data integration, in which you have to somehow manage the data, somehow you have to go and fetch the data, bring the data to where you're going to do the machine learning, so you have to integrate it. And there's very, very big questions of privacy, because you can say, okay, the data where it's stored is very private, protected, and then you're going to bring it onto your laptop or to some server in your department, and that server is not protected against pirates, so the data can lose its privacy. And then afterwards, you might say, oh, it's not serious, but in fact, they're going to look for some who was responsible for what they call the data breach, who took the data and used it for something else. We're going to have to, we will have to take responsibility, so we have to be at least aware of these things. The privacy we already spoke about. No. There we go. So, EHRs, fundamental source of big data in healthcare, a lot of information about a patient's health history. It can have something to do with demographics, all the diagnosis, the medications, allergies, immunizations, vaccinations, lab results, and even imaging studies. Okay. Slowly but surely, the medical profession, and all over the world, is now becoming equipped, doctors are becoming equipped more and more, so that your results of all the exams, all the diagnostics, all the medicine that you've taken is now quite easily recorded in apps, applications that automatically create these EHRs. And then one has to have a system somehow for collecting this stuff, but that depends on every country, every city, every province. So there's a lot of work to be done, but in principle, in theory, there's an enormous amount of data out there. We can use this for many purposes. We can improve patient care, we can conduct research, we can track population level health trends. And this data can come from public health departments, from hospitals and clinics, and even from private doctors. So I said today, if you start, it's starting with private doctors, it's going out to hospitals and clinics. If they provide the data to the public health department, then you can see we have an accumulation of very, very, very valuable data, which is potentially available and covers, as we said before, all kinds of different aspects of health. What about genomic data? So before, genomic data was something quite rare. Now the instrumentation has improved to such an extent that genomic data is very, very easy to obtain. And it contains the complete genomic composition of an organism. An organism can be, a microorganism from a bacteria to a human, right? To an elephant, right? And going through plants, trees, everything. It includes DNA, RNA, and epigenetic data, which has to do with expressions. You can use it to identify genetic variants, and these can be associated with diseases now, so this is interesting. And we can use what I told in the United States today, in some parts of the United States, becoming quite usual that a private doctor will use your genome or genomic data to give you a personalized treatment. It's quite possible today. At the moment, it's still not common all over the world, but today for cancer treatments, there's a lot of genomic, they take your genome, and they know, the oncologists know now which treatments can be adapted to different genomic structures, okay? This enables people tailor-made treatments. And there are many sources, okay, these are some very, very, it's internationalgenome.org, and then the National Institute of Health in the US also has a repository of genomic data sharing. But of course, there are very, very big issues of privacy and anonymization. This stuff has to be protected, but in some senses, sometimes it can be just plants or bacteria. That doesn't have. The genomes of bacteria, plants, and viruses, of course, can be shared and are shared. I'm talking about health, so it's more humans, but there are many of them. And then we spoke about medical imaging. Of course, medical imaging creates digital records. Right? So images of the human body are obtained using a lot of technology now today, which is very widespread. X-rays, tomography, magnetic resonance, ultrasounds are used regularly all over the world today. Even private doctors have ultrasounds, very simple machines, non-simple machine that moves around, and they put the emitter detector on your body that can measure. And it can be used for diagnosis, for treatment planning, and for monitoring, of course. And the volume is great, I showed you. yesterday, the volume is growing exponentially. It's amazing. Because the imaging technology is improving, and it's being used more and more in everyday clinical practice. So of course, the more it's used, and the better the technology. So you can take a single X-ray, chest X-ray data set can be 42 gigabytes, 112,000 image, 30,000 patients. Each image is 1024 by 1024 pixels. It gives you already 40 gigabyte image. Brain tumors, just 360 MRI scans already can give you 50 gigabytes. This is big data. This is big. There are images of melanoma for skin cancer. These are freely available. These are registered databases which are being created. And of course, there are many data on this here, just to show you that the data is becoming big. 130 in each. My laptop is 1 gigabyte. You need to put 113 of my laptops just to hold one data set. Okay? You see the data is pretty big. Of course, you cannot analyze 113 gigabytes on the laptop because you don't have. Well, actually, well, that's not true. I could like a terabyte. Okay, it's the same. In a terabyte, you can fit it in, but it's taking a lot of space. Just one single data set. So you see, data is not in shortage. And then we come to general omics data. So omics data is something that's developing more and more and goes beyond genomics. Okay? So it's all types of biological data, and it's listed to system biology. So system biology, I gave you reference at the beginning, it's the biology of systems, how biological systems function. Okay? These omics data correspond to the whole system. Okay? Includes genomics data about genes. If it's about RNA, then it's transcriptomics. And it's about protein data, it's called proteomics. And if it's about metabolites, which are important to create energy and other things, it's called metabolites. So these are all the omics. And the other omics, I'll give you some examples, like what in this topic. Okay. We can use this data to study the biological processes themselves. These, of course, underlie health and disease. And we can use, if you have the biological process, data about the biological process, you can use it to develop new diagnostic and therapeutic approaches. And I'll show you the machine learning techniques that are being used actually to do this type of stuff. So it's evolving very rapidly today. New technologies being developed all the time, and there's ever increasing amounts of what we call omics data. So in lecture 4, this is I have a couple of slides just on the different. I take each one of these omics, genomics, transcriptomics, proteomics, metabolomics, and there's also what's called radiomics, which has to do with radiology or imaging data. I've given this little explanation what each one is. It's good for us to know because we're going to be using these things, or somebody asks us to do some machine learning or some modeling based on these different omics data. You have to know that they exist and what they represent and what we can do with it. So I'll spend a little time, not too long, giving a list and an explanation of it. So it's okay to have data, but data has to be managed, has to be stored, it has to be managed. So it's important for us to know how is this, where is this data, how is it kept? We're not necessarily going to be responsible for it ourselves, but we can have access to data. It's important to know where and how data. So healthcare organizations, we've seen generate vast amounts of data from a number of sources in principle. So effective data management storage systems are critical to ensure accuracy, completeness, and accessibility. The researcher has to be able to access. So it's not enough just to store the data somewhere on a disk or somewhere on a thing hidden somewhere in a basement that nobody can access. It has to also be accessible. So there's a lot of considerations that come into data management. So usually these solutions are based on relational databases of some kind. And then we have what's called data warehouses, which big collections of databases. And now there's even cloud storage devices. So you could, if you have if you're a hospital or a clinic or a public health department, and you don't have your own servers to store and manage your data, You can buy storage today from Amazon, from Microsoft, and then you can use warehousing type of technology, which these are software systems, also hardware software systems, which facilitate the management and the storage of this data, and they can also manage the accessibility, which means there's a whole thing of security, of authentication and authorization. Who is authorized to use the data? How do you authenticate each user? There are a lot of very, very complicated problems involved behind all of this data. So it's not trivial like necessary. It's fortunate to be done. Okay, now, so we've seen the source, we've seen some of the sources, a list of the sources, we've seen how that data can be stored and managed, and now we're finally going to access the data, and when we get it, as I said to you before, the knowledge data process, we have to do pre-processing and feed. Why? Because raw data, and this I can tell you from experience, it's absolutely true, contains errors, missing values, and inconsistencies. So there's no way that you receive raw data that is perfect. It's not like when you're in school or university and somebody gives you an exercise, a programming exercise, or an exam or a project, the data is always clean, and that's not reality. The data is never clean. The data always has errors, always has missing values, and almost always has inconsistencies. And all of these need to be addressed before analysis. Why? Because the machine learning algorithms cannot function correctly if any of these things are present. Are present, they're going to affect the machine learning algorithm, and they're going to affect the quality of results. This is data quality. So we need to do pre-processing, which includes cleaning. Okay? And what are these things? They have a number of names, but in the end I'll show you the techniques of why. You have to identify first whether they are issues. How do I check inconsistencies? How do I check missing values? How do I check errors? Okay? So there's a whole profiling. You need to have a profile of what a good data should look like, more or less. It has to be positive. It has to be between 5 and 55 or something. Okay? If it's the temperature of the human body, it has to be between 35 and 40%. Anything below 35 or around 40 has to be signaled. You have to know that it exists, where it is, and then you have to decide what to do with it. That's my way of what to do. You have to clean once you've identified what's happening, you have to clean them, which means you either correct or you remove. These are not life questions. How do you correct? I'll show you some of the techniques. There is what's called imputation. If there are missing values, how do you fill in missing values? So with the data, one value is missing, basically it destroys the whole record. You cannot do machine learning if one data point, one data record has a missing value, because it will change completely the results of your machine learning. So one has to decide, either you remove all the data records. Usually these are lines, it's a data matrix. Usually the data matrix, every line is one data record. And in the data record you have columns. Every column corresponds to one measurement. Blood pressure, cholesterol, heartbeats, etc. So you can measure in a single record you have 5 or 6 or 10 or 15 or 20 or 30 measurements. Okay? And if any one of those is missing, you have to decide, do I remove the complete row, the whole record, or do I do some kind of computation? If I'm doing imputation, which means it becomes kind of interpolation, it's not as simple as all that. It's a strong assumption. You can be introducing a bias. Okay, so these are, and don't forget, the quality of the data is going to determine the quality of the results. Then there's a question of normalization. Normalization and transforming data is very, very important. Why? Because machine learning algorithms most of them do not work well. They don't converge. That's a question of convergence. They don't give good accuracy when the data has differing scales. Just say I'm measuring, I told you for each record I can have different measures. So I took the the glucose level, and I took the weight in kilograms. So the kilograms are going to be 30, and the glucose level is going to be 0.003 milligrams per liter. So if I'm going to put into a machine learning model things that have 4 or 5 orders of magnitude difference, it's not going to work well in machine learning models. It cannot deal well with very large differences in scale. That requires some kind of normalization. There are different ways of doing normalization. The way you do the normalization is also going to affect. You're introducing some type of bias, whether you like it or not. You have to. And then finally, one sometimes has transformation to convert data into some suitable format for analysis. So transformation would be you could take a logarithm with values are very high, and the log will give you values between 0 and 5. You have values of 10 that go from 10 to the 0, 10 to 10 million. It's better to maybe work on a logarithmic scale between 0 and 6. That will give you a reasonable transfer example. All of these techniques are necessary because they can ensure accuracy, completeness, and consistency of your data. So these are very, very important things. And if you say, oh, I'm looking into it's too much trouble, all this stuff. I just want the data with the machine learning. You're looking for trouble. You will find trouble. The trouble is just there waiting. You know that your results are not going to be good. I promise, I guarantee. I'm not sure about a lot of things, but some things I am sure. That bad data that has not been pre-processed and cleaned, will give you bad machine learning. You can't say, well, it's not my problem. You know, because the doctors, the clinic gave that data, that's their problem. No, it becomes your problem because it's your problem because you can use that data. You can put it into your machine learning algorithm and do your analysis and make your predictions or make your analysis, make your forecast. And it's become your problem, whether you like it or not. Okay, so that's why it's very important. And in fact, at some stage in the research and in the knowledge development process, one has to spend some time deciding what kind of treatment you're going to do. Once you've decided that you have what's called a workflow, we call it a pipeline, a data pipeline. Pipeline means the data comes in at one point and it undergoes various treatments, profiling, cleaning, imputation, normalization, transformation. Once you have your pipeline set up, then you can forget it, figure it out. Then usually it's good for the context that you're dealing with, the data set that you're dealing with. You get a new data set of different data, you have to make a new pipeline. Yeah. You'll see in pipeline now it's quite easy to set up this pipeline. It's not what you have to. There's work to be done. It's not, you can't just say, clean my data. Doesn't work. Maybe you can say to ChatGPT, go speak about it, clean my data. I wouldn't trust what it is. Okay. You have to do it yourself. Okay? And this requires something based on experience. And if you don't have experience, you try and you see the quality of the results. You have to have some way of determining the results of good quality. You can compare known results with publications, with experience of doctors, and then there's some way of measuring, knowing whether the results are good quality before you start to venture into your limits. So there are ways of deciding, and if you don't know, as I say, you try something which seems reasonable, check the results. It looks reasonable, it looks good to you, it doesn't look good to you, you try something else. Anyway, it's good to try 2 or 3 different ways of cleaning, ways of imputing, ways of normalizing, to be sure that in the end you have something that gives you good quality data. So it's not, I cannot say to you do this, that, A, B, C, D. I'm sorry, it's not, as somebody says, we're dealing with living, it's life, it's the real world. The real world is not AX equals, it's not 5x equals 10. Remember that, it's not deterministic. It's statistical because there's variation, random variation to some extent, and that's why these things happen. So, very quickly on each one of the points, but this is what is data cleaning? You have to identify and correct the errors and the inconsistencies in the data. For example, one often finds duplicated images. For some reason, results are duplicated, double or triple. It's just when results were registered or recorded, somebody copy-pasted twice or copied something or something. You have to handle missing values, and you have to format data so it has a consistent structure. The algorithm needs to have data tables that have the same dimension. Every row has to have the same dimension, for example. Okay? You cannot have some rows that have 15 entries and another row with 25. Okay? That means your model doesn't know is it a model with 15 points or is it a model with 25 points. Okay? So this is very essential. So it's the first step in the data processing pipeline, data pipeline directive. It can include things like typos, Just somebody can mistype, get the wrong value. Bad formats, missing values, absolutely essential to ensure that the data is accurate and reliable format. So that's the very, very first point. You cannot start, do not start, even if your cleaning this stage concludes that everything is clean, it's important to do that. Even if you're sure, this you have to check, you have to be suspicious. Because this determines all the rest. If this is not well done, all the rest will be there. Imputation or filling in of missing values is a very, 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 very important. Missing values occur for a variety of reasons. Data entry, for example, a patient who refuses to answer certain questions. Patient says, oh no, you want to know my weight? I'm sorry, it's personal. So there'll be missing data. That's one example. Sometimes the instrument that was measuring has some problem and it misses some of the values. There's always a reason for missing values. You'd be surprised how many missing values there are in real data. Okay, a lot of imputation techniques. And unfortunately, the best technique will depend on the specific data and on the intended use of the data. So I cannot say to you, well, that's missing values, do this. It's not as simple as that. There's a number of techniques and we have to choose. So some of the techniques are the following. You can use mean or median imputation, which is you can replace the missing value either with the mean or with the median. Okay? These have different implications, the one that you use. Because median we know, well, if you could trust your statistic, median is a robust measure of central tendency. Mean is less robust because it can be very strongly influenced by extreme values. So if there's some extreme values, for some reason somebody made a mistake and put a temperature of 100 and you take that into account, it's going to skew, it's going to move your mean to larger values, whereas the median will not be influenced by a single value that has a large value. Okay, so that depends on the nature of it. One often uses more complicated ways of interpolating. One can use what's called KNN. KNN is an algorithm. It's a very simple machine learning algorithm, one of the first ones used, which is able to predict missing values based on the neighborhood. KNN means K nearest neighbors, so it takes the nearest neighbors to your point and computes the average of the nearest neighbors. So it's a clustering algorithm to compute averages, to compute representative values. So that's sometimes used, much more sophisticated than doing median. It's taking into account the vicinity, the neighborhood of your data point, and getting something that's a good average. It's missing, so you have to do something. You want to do something reasonable, fill it in. And then one can use more complicated methods based on regression models and many other statistical techniques to estimate these missing values. Sometimes these relatively simple methods might not be reliable in the context of your data, and one might need to do extra things. And this subject, you'd be surprised, of data imputation is still a research subject. People are still doing research on what kind of imputation one should do in the context. So as I can say, so how do you do it? You start with something simple. If it seems to give you good results, you say, okay, that's correct. And if not, you try something else, and eventually you try one or two, and you compare the results between the two, and you choose between the two or between the three. It's almost always that. Third thing, normalization, very, very important. The process of transferring the data into a common scale. And I said when there are many different scales, many orders of magnitude, you would like to put all your data onto a common scale. It's important for most machine learning algorithms because they're very, very sensitive to the scale of the data. And then, once again, there are a number of normalization techniques, or basically there are two, but you can make variations of these two. And the choice will depend on the specific data and the intended use. This is very vague, but it would be dishonest for me to say, do this, do that, because I don't know your data and I don't know the intended use. So I cannot tell you, do this or do that. One has to try one or both or three and compare. Okay, that's only advice that I can give. Oh, the main types of data normalization was called min-max or 0-1 scaling. So you transform all the data. You remember, I have a patient, and you have the weight in kilograms, and you have the glucose level, and you have the heartbeat, and you have whatever. All the clinical data. You measure at the scale of completely different. So one wants to bring them to 0-1, so it's easy. What you do, you subtract the minimum from the value of all the patients. So it's the weight. Subtract the minimum weight, and you divide by the max minus the min, and that will give you automatically a value that is between 0 and 1. The minimal value, min minus min, in the numerator will give you 0. The maximum value will give you max minus min divided by max minus min, will give you 1. So all your data will go within 0 and 1. That's what's called min-max scaling or 0-1 scaling. And then the problem with min-max scaling is that if you have some values that are negative and some are positive, that can happen in different circumstances. It doesn't respect negativity and positivity. Everything becomes positive. It's a mapping from R into 0-1. Okay? If your values are negative, they'll still give you a value between 0 and 1. Standardization, or sometimes called normalization, scales the data at a mean of 0 and a standard deviation of 1. So it means you take your value, you subtract the mean, and you divide by a standard deviation. So min-max is easy, it's xi minus min of xi divided by max minus min. 0. Standardization says I take xi minus, let's call it average mu of xi divided by sigma of x. That preserves, it maps from R into R, which is good in a way, but at the same time it normalizes. In other words, it tries to put everything around a single central value and having a standard deviation of 1. So it's a way of normalizing. You see, these are completely different, huh? They both have addition. They are both absolutely indispensable for the machine learning algorithms, but they're quite different, huh? Look at the range. The range of your map is different. Okay, this is going from R into 0-1, and this is going from R into 1. Okay? It's a mapping M from R into 0-1. This is a mapping M1, M2 from R into 1. So mathematically, because we know mathematics, we realize that these things have completely different characteristics. Okay? And which one you choose? As I say, it depends on the specific data and the intended use case. You don't have any idea, you don't know. You try both and compare and look at the final result with machine learning and say, well, this one seems to work better for the data that I have and for the machine learning algorithm that I'm choosing to use. Okay? All this sometimes is very important to keep negative and positive values in your model. Sometimes it's not so important. You can do it between 0 and 1 and make it work. This is very complex. In fact, I can't give you a rule. There's not a theorem that exists, or a method. Okay. That's how it is. But at least you must know these things exist, and that's just the method. So anyway, I just show it's very easy to do. In fact, so okay, I have some example with time actually. If you want to do it with max standard, it's very easy. You just you have your data, you divide, you say, my scalar here is min-max. I'm doing this with cyclic And then I just say scale M is scalar M, and I use the method flip transform, and I add it to the data. Then I decide I want to do scalar as an X, and the stabilization, I just define scalar as a standard scalar, and I can have a version of my data which is standard scale, that's the version, scale M is min-max scale, scale S, and then I can do my data analysis on the one or on the other, on both, and compare. So you can see, for the technique it's easier, and the technique I'm not going to spend any time. For me the technique is just, anybody can get it. You can give this to anybody, you tell, I want to do this, I want to do that. You just have to go onto Scikit, learn, go to the doc, look for min-max, look for scaling, and there'll be these examples with very easy to do. So that's why I said I'm not going to, in the week of the time. If we have time, we will go into how to use it. I'll show you some examples, but here we don't have time in a simple course, we cannot go into depth. But we can give you the ideas and give you the tools that you can go into depth. Okay, the final point, which you might say, okay, it's not our problem, confidentiality is active, but in fact, I say because getting the data, you inherit all problems with data. So if there's trouble, they're going to come and say, oh, where was the leak? Whose data was the pirates, they attacked who? They attacked the data, where did they get the data? The pirate. Or, if it's you're working for an industrial firm, there's industrial espionage, somebody wants to take your data and your results and use it for something else. These things happen. This is not theory. And even though we don't, as data scientists or machine learning people, apply mathematicians, we're not going to do the confidentiality of standard proof. We have to know that it exists and the different. So there are many ethical concerns. We're going back to ethics again. You see my philosophy coming back. Because there are issues of privacy and consent, especially for use of medical data, that need to be addressed. And we have to ensure that the rights, we call them patient rights, are upheld or preserved or respected in the age of big data. So we spoke a lot about these things because obviously very important. Confidentiality is very important. And then there's the whole issue of cyber threats. So cyber attacks on medical imaging systems, for example, and other systems as well that utilize big data are a growing concern in the healthcare industry, not just medical imaging, general medical data. Because the health organizations are relying more and more on these digital technologies, storage events of very, very big volumes of damages, they become more and more vulnerable to various types of cyber threats. And there are a very large number of potential cyber attacks with very, very serious implications. Okay? I don't know if you've heard. Hospitals have been locked down because of cyber attacks. They sometimes ransomware. They say, we lock the data until you pay us $1 million. Okay? You don't have any of that. You don't have access to the data. Basically, the hospital stops functioning. Okay, this is very, very bad. So, I'm not going to go because the cyber attack is a long list. Ransomware, data breaches, distributed denial of services, model corruption. They can even corrupt your model. They get hold of your code, they can change your code. The pirate can change your code. Man in the middle in cyber software. I don't know, I'm not an expert, but this is a list. If you want a list of all the cyber attacks. And then there are ways of prevention. Okay, so there's some basic rules of good conduct which can prevent talking. One should use encryption if possible, if necessary. One should control access. If you have data just lying around on a GitHub, everybody can access it. And if that data has security and privacy considerations, of course, you should ensure that it's not publicly available in no public use. One should keep your software updated if software is not updated at pirates get into the machine. One should train the staff about phishing and how to say, people send you emails saying, I'm responsible for your healthcare data, please send me the password. And it turns out that it's not responsible, it's a pirate, and somebody has access to the network security. And one can use actually today, they're using more and more AI. They're using machine learning now to detect and to respond to signals that tell us that there's a potential of cyber attack. So, okay, so that's a whole, there's a lot of good jobs available in cybersecurity. If you want to do something, that's different. You've got to do cybersecurity. Alright, so that's the end of what I wanted to say about the data. But now we're going to start to get on to what we came here for, right? So what to do? There we go. Okay, so now we need to do machine learning without doing machine learning. Okay, because you know, as I said, it's an hour and a half or 2 hours or 3 hours of lectures, because we cannot learn a lot about machine learning. Or I could teach you show you one or two techniques of machine learning, and then there's like 300 others that I don't have time to do. So in order to jump over that, I'm going to say to you, well, as I said, there are good books available on the internet. There are good lecture notes, some of which I've written myself, which you can go and take, and everything that you need to know is there. Okay? What you don't know is how to use these things. So I'm going to speak about a rapid overview of algorithms and how to choose, what to use, how to choose. It will be a bit vague, but at least it's some initial guidelines will help you. Afterwards, the choice will always depend on the data. There's nothing I can do. What's very important is how to evaluate your model performance and perform what we call validation techniques. So these evaluation of model performance and validation are necessary for any machine learning method. So what's good is instead of, I don't have to teach you individual machine learning methods, because this corresponds to any, it's valid for any and for all machine learning methods. Whatever machine learning algorithm, software, method you use, you're going to need to evaluate the performance, basically the precision, the accuracy, okay? And you're going to need to do what we call validation. I'll speak about validation more detail, because that's a very, very, very important stage of any machine learning work, is the validation. So afterwards, I'll show you some uses this quickly, and then some use cases, and then in the next lecture, either we start, I don't even have time today, but we'll do that tomorrow morning. We'll speak about applications of machine learning for health sciences. So, and in the application section, I'll speak about omics data. So that will come as an application, because here I'll show you a list of some of the most important machine learning algorithms, and you'll see that when we speak about application, you'll see that almost all of the things that I speak about here, you'll see how they are used in the application, or where they're used, not exactly how. But essentially, we cannot show you like that. We don't have time here to really show you the code and the thing. But you'll see that everything I mentioned here will be mentioned also directly when we speak about omics data. So, let's start. Machine learning algorithms. So this is a big, big, big subject. I told you. There are hundreds and hundreds and hundreds of machine learning algorithms. Now when you start, even if you're doing it for a while, you're going to be lost. That's normal, okay? First of all, I call it looking for F, because I explained yesterday to some of my students. Well, what is machine learning really doing for a mathematician? It's pretty complicated, because machine learning is very conceptual. Then the detail. It's like hundreds of hours to learn. But machine learning is very simple. You have input data and you have output data. I said we need data. Data has inputs, output to outputs. Output, I said, it can be a value, it can be many values, it can be yes, no, it can be cancer, no cancer, it can be hot, mild, cold, it can be high danger on the other side, medium danger, low danger, etc. These, we'll call these X. In fact, often we'll put them into it will be a vector X. And these we'll call Y usually. That's the notation. Y can be a vector also. And this is a vector. That's something, there's an F. That's why I call it looking for F. Machine learning is just looking for F. F is going going to be the mapping, which maps the input to the output. If we had an equation, if the system was simple, we'd say, okay, well, that's just, you know, it's an SIR system. F can be a system of, okay, we can describe it. But why do we use machine learning? Because since we don't know F we know. So the machine learning, in fact, is going to give us an approximation of F that maps F hat. In statistics, we always put a hat when we want to denote it as approximation. We don't know F. We're going to try and approximate it as best as possible. And it's going to map X, or vector X, into Y. But it's not going to be Y, it's going to be an approximation of Y, right? Because if we knew the F, as I said, if we knew the F, then we would know when we were born, when we were going to die, and everything in between. So we don't know that. We don't know F. Right? But we can hope, thanks to the data, and thanks to machine learning techniques, to get some kind of good approximation of that. And all of machine learning mathematics is, well, all of machine learning. I'm talking about supervised learning in this case. Supervised learning, I said to you, supervised learning supposes we have data pairs, input, output pairs. For every X, I have a Y. Then I have a number of samples, so I have a number of X's. And X itself can have many features, many properties, many blood pressure, glucose, heart rate, etc. Okay? Just take human clinical data. So the X in fact is a matrix. I could even put X like this. To make X a matrix, I put a double line in. That makes X a matrix. That means X is a matrix. In fact, we're looking for a mapping from X into Y. Or that's been demonstrated. So that machine learning is just looking for mappings. I won't say what it is because in fact, usually people mappings are so complex that they cannot describe what they became with equations. Some machine learning methods use equations, but those are very, very rare. Those are what we call regression methods. Regression methods, in fact, give you an equation for F. That's why regression is one of my favorite methods, because for a mathematician, it's nice to have an equation. Regression will give you an equation for F. And what's good about an equation is that we speak about trustworthiness and transparency. Equations are transparent. That the most transparent, the most simple to understand machine learning method in the world is just called regression, because it gives you an explicit formula. That is the only machine learning method that gives you an explicit formula. There is no other machine learning method that I know of that gives explicit formula. So regression, which is old, it goes back to the last 18th century, long time ago, like this. Regression is one of the first machine learning techniques one should try if it's relevant to your data techniques. We'll speak of it because it gives you a lot of interpretability. So this is supervised learning. There's also what's called another category. So supervised learning, somebody is supervising. Unsupervised learning, you're all by yourself in front of the data. Because unsupervised learning, we don't have input-output pairs. We're looking for patterns in the data, things that are similar to other things. Usually it's similarity. Unsupervised learning usually has to deal with what's called clustering. We're looking for clusters of things that look like other things. In other words, in the X's, we just had X and Y. So within the matrix X, you understand X is a matrix. It has columns, blood pressure, glucose, and it has lines, patient number 1, patient number 2. Patient number 3,000. Okay? So it's a matrix. We're just looking for patterns in the data because we don't really know. Very often, when I've been consulting and helping people solve problems, it's not clear. We don't know what Y is. It's not obvious always what Y is. Y might be something that's inside the data, but there's no explicit value of Y. I cannot separate it. If I have inputs and I have outputs, I just have data. And then you can say, well, what do I do? You can do unsupervised. Okay. And then the third category is reinforcement learning, which is much more complicated, which uses, it's what's called semi-supervised learning. At the same time, it needs some type of input-output, and at the same time it can generate its own outputs and give or rewards. It works on rewards and punishment. So if it gives itself rewards for reinforcement learning is used in very special contexts like team folding, like games of Go, games of chess, to learn to play games. But used like robotics, autonomous driving, reinforcement learning is used a lot. These are special contexts that these are complicated. And then the latest fashion for self-supervised learning. This means you don't need it. It's going to take care of itself completely, which is quite unbelievable. But that's called generative transformer models. This is ChatGPT. This is large language models called self-supervised. I'll mention them briefly, so we don't have time to study and understand self-supervised learning. But until 2-3 years ago, this was not even noticed. All the graphics that I found on the web, it's step 3 types. Supervised and unsupervised reinforcement. The fourth type is very, very, very recent now. ChatGPT came out 1 year ago, a bit more than 1 year. 1 year and 5 months, in December 2022. So things are moving. Self-supervised learning is becoming very, it's becoming everything, and it's we have to be very careful. In the end, at least most of the supervised learning, which is a lot of what we do, is looking for error. So you can keep that in mind. It helps you to understand what we're doing. At least you have some kind of theoretical basis. So, self-supervised learning, it combines regression and classification. So what is the difference between regression and classification? It's quite important to do these, to separate these families, because afterwards it will help us to choose the methods. Every family has a certain number of methods, machine learning algorithms, machine learning methods that can be used. So even if you know this, it's good to think about and identify the type of problem you have. Once you have the type of problem, then it really restricts the number of possible approaches and machine learning. So regression is quite easy. What I said to you, we have labeled data, x and y pairs. Okay, they can be in some vector spaces x plus y. And the x's are called data samples, the y's are called, which we call them labeled, but it can be a value, it's not necessarily labeled. We call them labeled data, which means every x has some kind of outcome tree. And supervised machine learning is looking for the model y equals x. And you see there's a w. The w are what we call the weights. These are the parameters that the machine learning is going to find f. Well, it's going to look for a set of weights that are in general. Weights in terms of regression, it's just the coefficients of your regression equation. It's the simplest case. But as things get more complicated, the weights become more complicated. You cannot write very explicit formulas for the weights, but in general, it's going to adjust the weights in order to obtain a y hat that's as close as possible to y. Okay, so that's how it's going to measure its performance. It's going to measure success by saying, well, I've adjusted w. I don't know, obviously initially I don't know w, so usually most of these algorithms start with w equal to some Gaussian random variable, some distribution, just randomly chosen values. You choose w completely randomly. You could even choose w equal to 0. W is a vector. W can be a dimension 10 to the 9. W can be very, very, very big. In linear regression, W is 2-dimensional. Beta 0 plus beta 1x. Okay, that's the simplest case. Neural networks, W can be very good, dimension W can be very big. And then the supervised machine learning is going to use a performance metric and some hypothesis there to measure how well it's doing. So the model there will map x into y and approximate, get that function like that. So that's what's called regression. We have x and y being real numbers. X is a matrix of real numbers, and y is a real number. So we're looking for quantitative value. Classification, on the other hand, is exactly the same, except now that y is in a discrete space. It takes values in n, okay? And anyway, usually n is just a number, but it can be black and white, it can be, as I said, benign, malignant, if it's cancer, it can be 1 or 2, but anyway, if it's benign malignant, you can say benign equals 0, and malignant equals 1. So you map it into the space 0 to 1. Okay? So it's the space of natural numbers with values in 0 to 1. So classification is the same type of supervised learning. We have pairs, we have X's and Y's, you have patient clinical data, we have about the thickness, the size, the color, the dimension, the number of cells, and then you have here a diagnosis, benign or malignant. Okay? So instead of having a number at the end of your last, as your Y, you have a category. So it's mapping of real numbers into categories. But it's the same type of problem mathematically, except that the algorithms we use are the same. I'll show you the list of algorithms most commonly used to solve classification problems. They're not special algorithms, machine learning methods and algorithms to solve. Those are the basics. It's a lot of what we do is this. So what are the this table is very valuable. This table doesn't exist anywhere except here, and I think this is in my book because this is copy pasted from my book. So I found that I needed this kind of table to help students, researchers to find their way. People who don't have enough experience in machine learning or have not been solving the same problem for a long time to find their way through the forest. So I denote regression by R, classification by C. And I have the simplest models for, you see, I'm going from, I have a column that's called complexity. Complexity turns out to be very, very important. The more complex the model is, the more imprecise in some sense, or the more imprecise in terms of what we call prediction. The performance of the we want the model to have good predictive performance. In other words, it's going to learn on the data that it knows, and then you're going to use it to predict or to interpolate or extrapolate on data that's been unknown. So in fact, you're not really interested, why you ask, in how well y hat came to y, because that's your training data. What you're going to train, you're going to iterate enough times in your training or use a method of sufficient complexity. You know, if it's a regression, you're going to put more and more terms into your regression. Okay? Imagine, I'll show you the example very soon. You'll see what happens when I use too much complexity. In other words, what happens is instead of finding, say I have a linear train, but my points are like that. Okay? If I use a high enough degree polynomial, instead of interpolating, I'm going to go directly through all the points. In fact, I'm going to adjust my model to the noise. There's noise in the data, and if you push the complexity of the model far enough, instead of finding the underlying trend, you're going to be modeling the noise. And if you model the noise, the difference between y and y hat will be 0, very close to 0, because you're exactly going through, you're not interpolating between, but you're going to every point. Okay? That's because you're pushing the complexity. That's what I call complexity. Okay? Using a higher order model, which means your model is more complex. It has to do with the order of the model, if we're talking about regression. In other methods, it's not like this. So, it turns out, and I'll show you why, that one should always prefer low complexity models, because the low complexity models have better, what we call predictive performance. They predict better. They don't necessarily learn the best y hat, but when you use data that was not used, that has not been seen, or unseen data, that's the idea. Why are we making these models? We want to find this mapping. We want to find this mapping, not on the data, not to use on the data that we already have, but to use on data that we don't have yet. So we can give it to somebody, and that somebody can use it to make some kind of prediction, make some analysis, decide some kind of public policy, I'm going to do this, I'm going to do that, test it on unseen scenarios. So that's why the complexity is important, because the lower the complexity, I'll show you, this is mathematics, this is a mathematical theory. The lower the complexity of the model, the better its performance in prediction. Wow. So, I have this model, important model. You can choose your methods. I have a regression problem. I can choose between linear regression, classification and regression trees, support vector machines, neural networks. But you see, the complexity is increasing. If I'm talking about classification problems, I can choose KNN, naive Bayes, or logistic regression. And then some of these methods you see can be used for both regression and classification. So here I have increasing complexity, and then well, it's also increasing. The neural networks are the champions, because they're the most complex. Okay? Which means they can do incredibly well in training, but sometimes they can do very badly in prediction, in what we call testing. Training, you can train it well. So, this has to do with what's called the bias-variance compromise. I'll explain that there's a mathematical combination, and these are mathematically proven facts. It's not just I'm saying it's not politics. So this table is very important because here I assumed 1, 2, 3, 4, 5, 6, 7 or 8 methods that are the most useful and the most commonly used methods in supervised machine learning. There are many other methods which sometimes have been used and can be used and are used for very specific contexts. And why would we use some other method? Well, none of these methods seems to perform well on my data. I cannot train using these methods. Then maybe I can look more there or what's called. There are many other methods. I working with elastic nets, SMART, there are thousands of other things I could mention. I'm not going to mention. You should know that in the whole hundreds of machine learning methods for supervised machine learning, whether you're doing regression or classification, you can choose among these methods, and these are very good methods because they are well-known methods, robust, that perform well, and you can use them without any worries whatsoever for your program. Okay? You can say, but which one should I choose? Okay. If you don't have a reason to choose a specific one, I would say always we look for the method with the lowest complexity that gives satisfactory performance. Okay? We have some kind of idea the performance accuracy we want. Afterwards we have to forget how we measure performance accuracy. That's also a big question. And then among all these methods that give us satisfactory performance, we usually want to choose the one with the lowest complexity. Lowest complexity means more interpretability, and it gives better performance. I'll show you when confronted with unseen or what's called test data that is not in X. You can remove that because obviously when you give your model to what's the model, they can use it sometimes. So that is supervised. Unsupervised, I said there's no why, there's no label, there's no risk. We call this explanatory variables, and these we call response variables. There's no response. There's just a bunch of animals. And unsupervised learning is going to turn, and it's going to group all the birds together, all the fish, and all the dogs and cats. For example, this is a stupid example. What's not so stupid? For computer vision, it can be important. Which we have to categorize specific cars, the truck, the pedestrian. Your Tesla's going to drive down the road, but you know, in front of me is a bicycle, is it a motorbike, is it a bus, is it a human, etc. Cancer cell detection, of course, very important. Unsupervised learning. So it's used for clustering, for identifying patterns. It's also used for dimension reduction. So we don't have time to go into it. But for example, when one uses spectroscopy, we have spectrometers that are used for analyzing chemical compounds. A spectrometer gives an X. I don't know how many samples you have, but I'm looking at the columns. The columns can be have up to 2,000 columns. A mass spectrometer can give you 2,000 independent variables. But clinical, we say, okay, there's the weight, there's the heart rate, the cholesterol, etc. Mass spectrometry can give you up to 2,000. So in that 2,000, you're going to have a model of such complexity that it's going to be basically unusable. But there's most probably, very often, a space of reduced dimension. In other words, you can choose a certain number of the polymers of X, which are the most important, which carry the most information. And so unsupervised learning can be used to find a lower dimensional space which somehow captures as much as possible of the information that's in the data set. Okay, so this is used a lot in some contexts, and I'll show you some differences that are used. Okay, so, what are the methods? So, like I made a table for supervised learning, I can make a table, the same kind of table for unsupervised. Okay, so, depending on the task you want to do, clustering or dimension reduction, there are a certain number of methods that are used which have low to medium, and medium to high complexities. Once again, for dimension reduction, we have this factor of the complexity, and then you have the type of task you want to do. And if you're doing a lot of clustering is usually done. One usually tries with k-means, one of the dendrograms of tree-like structures. As I said, I don't have time to go into these, but each one individually, as I said, you can find information all over the place on how to use, which are the algorithms, etc. And then for dimension reduction, one of the major things that's used is topological analysis. And then there are specific types of neural networks which do dimension reduction. They call them encoders. There are dimension-reducing neural networks which can also be used. So, okay, if we have time one day, I'll come back and tell you all about this. Note, however, that the difficulty with unsupervised learning is that the interpretation is always dependent on the context and should, if possible, be based on some knowledge or some expertise of the domain. So if you're doing unsupervised learning for cancer detection, you should always have an oncologist, a doctor next to you. If you're doing something for, something else, which is very specific, you should have a person, an expert in the domain, to have a look and to tell you whether your clustering algorithm has produced something that is good. Once it produces something that's good, you can give it any biopsy that hasn't been seen that wasn't used for training, and you can be confident that the clustering that your algorithm has produced can be used on unseen data. So there is a question in unsupervised learning. As I say, we don't have time, of course, to go into it, but you can find a lot of different answers where the interpretation is not as simple as, because it is subjective to some extent. And then finally, reinforcement, well, finally, that's the second time. I don't go into this, I'm not an expert. This is machine learning, I'm not, this is robotics, self-driving cars. You can find lots of nice examples of reinforcement learning and how to use them. This goes way beyond what a mathematician does. It used what's called agents, actions, environments, and rewards. So it's a system that generates examples by itself. It tests itself. And if the test is positive, it gives reinforcement to use more of that than to use something else. And there are a lot of reinforcement learning models because we use a lot for very, very sophisticated patterns. And now, what's new is these guys. These guys are going to are changing our lives. I don't know if it's changing for the better or for the worse, but okay. A major technical evolution for society and evolution and science. So, we like it or we don't like it. For the next couple of years, until we find either a reason to keep them or a reason to throw them away, generative or transformer models. One of the major examples is ChatGPT, but now there are many others. Okay, ChatGPT is just the name of the generative pre-trained transformer, which was created by OpenAI. Generative means it can generate its own output. It doesn't need input-output pairs. It generates itself. So it's why I call them chat bots. A robot here is a robot that can chat. It means you can have a conversation. You get the impression that it's intelligent because you can speak to it for respond. But it's a robot, don't forget that. So this robot, this chatbot has become ChatGPT, it's become Gemini, it's become Llama, it's become a lot of other things which are not there. So they're based on it's a neural network, right? It's a deep neural network. Okay, we'll speak a little bit about neural networks. Unfortunately, at that time, neural networks are fascinating. We could spend tomorrow. We'll speak a little bit about neural networks. That's what's called an encoder decoder architecture, and it uses lots of sophisticated things. ChatGPT itself, how many parameters? W. I said the vector W can be big. 175 times 10 to the 9 parameters. Okay, that's a big model. If I imagine a linear regression, polynomial with 175 times 10 to the 9 terms. That's what you're looking at. Okay, it's crazy. It's completely crazy. But that's what's become possible today. It costs approximately, they consider that to train, to find good values of W, it costs about $5 million. That's basically the electricity that's used. It uses a lot of electricity and very, very, very powerful. GPU-based computers are doing this now. So the people who are training these, who's doing it? Well, it's Google and it's Facebook and it's NVIDIA. These are the richest companies in the world. These are the only ones who can afford to train these guys. Research institutions, researchers don't have the money. It's too expensive to train. So in some sense, I said to you that there's probably big models being imposed on the rest of the world. Unfortunately, that's reality. Though things are changing to some extent. So these are out of the reach of you and me to some extent, to a large extent. But they claim that it's going to change society, it's going to change education, it's going to change science. We have to see how it. The bad points is that they have what we call hallucinations because they're not very intelligent and they cannot guarantee the veracity of the fact that what they tell you is true. They're very unstable, very difficult. The models of 175 billion parameters you can imagine, you cannot interpret. It's not very interpretable, right? You cannot say, well, this coefficient W1 has an effect on that and W2 effects. Okay. You cannot relate the model coefficients content. These are very, very, very black boxes, very black. Not transparent at all. Okay. So, what I said before, this morning and yesterday, we're long way away from interpretability, explainability, a long way away from trust. So if you ask me today, do I trust these guys? No, I do not trust them because I'm a scientist. If it's telling me I should buy a green shirt and not a red shirt, okay, I'm ChatGPT, you really should have a red shirt. I say, I like this and I like this. Definitely should buy a red shirt. So I don't buy a red shirt if I make a mistake. Okay, it costs me a few bags. I don't like it, I'll give it to somebody else. I use it for something else. But we are scientists, and scientists cannot play with red shirts and green shirts, right? We have responsibility to the society, to the people, the government, to the world, right? And so for science, this is no good. Today, it's still no good, okay? And the big problem, it's very eloquent. They speak beautiful English or beautiful Thai. They write you give it a research question. Whatever question you give, almost it'll give you a response. And not that, it'll give you a very convincing response, It's written very nicely. It pulls out publications, citations. Very often the citations are false citations. It's generated, what I call generative. It's generating the citations. It's generating the words. It's generating everything. Where's it generating from? Well, I didn't tell you that these use very, very big database. The training data, the dimension of X is hundreds and hundreds and hundreds, even thousands of terabytes. It's almost petabytes of data. The dimension of text is so big, that's why it learns. It gives you something that's quite convincing because it's learned. It's been trained on enormous. Google, of course, can give it all the data that Google has, and Google has a lot of data you can imagine. Okay, so you understand, these guys are well trained, and then they train to generate text. That's why chat. That's why we like it. They don't give you a number, they give you a story. And very often the story sounds very good, but when you start to dig into it and look at the hypotheses and look at the conclusions and look at what they propose, you often find, especially it's a complicated question, not should I choose a red shirt or a green shirt? You start to dig into what they propose, and very often you will find that there are hallucinations, that was illogical stuff that's not right, it's wrong, it's bad, unfortunately. I don't say that you shouldn't use it, because I see if you can break up your problem into small pieces, and some piece you have an idea of what it should be, but you want to, maybe express it in a better way. Give it to ChatGPT, it will give you a very nice expression of your problem, and because you know more or less what the hypothesis should be, what the method should be, what the kind of conclusions, you can have some kind of critical appreciation of what's there. If you don't have in science, the rest, you do what you want. Use ChatGPT, you say, I want to travel to Bangkok, what should I see? It's going to give you a great list. Try. I'm going to Bangkok tomorrow for 2 days. What should I go and see in Bangkok? It will give you a beautiful list. They give you the list and the directions to get from one site to the other. It will give you a really nice itinerary with recommendation. And what are the great shots for my clothes in the area? Fantastic. It's better than Google search because the right make you a list point by point, it will give you directions. It tells you a beautiful story, and if you get a tour, if it tells you to turn left, you should turn right. Not the end of the world, you go to Google Maps and Google Maps will fix it. Okay? But if you're asking it to propose some kind of answer to a research question, I warn you, I warn you again. Until today, these methods are not reliable. They are no good, and in addition, they are definitely not interpretable, and they are not transparent. That's not going to change. Whatever you do. So be very, very careful. You're going to use them, everybody use them. Use them as a research assistant. When I have research to do, and I'm lazy or I'm old and I'm tired, and I did that 20 years ago, but now I already have that patience and strength to do it, I'll give it to my research assistant, but I know what kind of results should come out. I know more or less, I don't have the time and the patience to go through all the writing research. If you know more or less the grosso modo what's to be expected, you can give it to ChatGPT, because sometimes the student will come back and I'll say, that's great.